Alright, hello and welcome to a new topic called sets. And I'm very excited to teach them to you because they're very, very powerful and very, very important. So this guy named Georg Cantor invented this concept called a set, and the goal of them was to put them at the very bottom of the chain and just start with these things called sets and define everything else in math with them, so that everybody's on an even playing field. Everything has foundation and it all works out. And everybody thought that was a really cool idea, and they've just been rolling with it ever since then. So sets are everywhere in math. Very, very important. And it's a very generic idea because it's supposed to define everything. So let's start simple. So a set, all a set is, it's a collection of objects. It's just I'm telling you right now that I have these things, and that is what makes up my set. So legitimately you can put any objects inside of a set, even all the green M&Ms in your favorite Save Mart or in the entire universe. You can make a set out of those and mathematically do stuff to it. Okay? So yeah, the objects in a set are called elements, and you usually use curly braces to define stuff. So here's a set called C, and I can put a bunch of objects in here, and they're all comma separated. It's here's an object, here's an object, here's an object. You just fill it all in, all of C's objects. They go in here somewhere, separated by commas. That's all a set is. C's elements go here. And then you can do cool stuff with sets too. So this is called roster notation. It's you're a teacher and these are all the students in your class. This is a roster of all of them. You're just listing everybody out that belongs in your set, all right? When you list it out, it's called roster notation. So here's a set A. It has the numbers 1, 2, 3 in it. Pretty simple, right? Here's the set B. It has 2, 4, 6, 8 in it. Not too bad, right? So one interesting thing about sets is that it does not care about repetition. So the set 1, 2 is equal to the set 1, 2, 2, 2. Duplicated elements are not important in sets. They just kind of go away. These are the same set for our intents and purposes, okay? You can have multi-sets where these are different, but we really only care about normal sets in this class. So that is sets and roster notation. It's all pretty simple, right? It's just you're listing down some stuff. I have this jumble of things called objects. All right, so this is A. It has 1, 2, and 3 in it. You can talk about individual pieces, individual elements of A by using some notation. All right, so for example, Venn diagrams, believe it or not, it's technically using set theory. So here's a Venn diagram. This represents the set A, right? It has 1, 2, and 3 in it. It does not have 4 in it. Here's 4 outside somewhere. But A has 1, 2, and 3, and 1, for example, is an element of A. We can talk about who's in A and who's not in A with this little symbol. It's the Greek epsilon, and so read it as in. 1 is in A. Okay? That's the idea. So 1 is in A is a true statement, and you'll just read that as in, and you can put a little slash through it and read that as not in. Just some notation. So 2 is in A, so is 1, 3 is in A, but 4 is not in A. Okay, that's how you'll read that. Just talking about what is in this set. And I promise this is very useful. All of mathematics is defined this way. You can have a set that has nothing at all inside of it. So a set B. And the way that you represent emptiness is just you can put some parentheses without anything inside, or you could put this symbol. That's a 0 with a slash through it. That just means that B is the empty set. There's nothing in B. No elements. You can have both finite and infinite sets, because in math you have a lot of infinite things. So a finite set is just a set where you can list them all out and you'll end eventually, right? It's either a set that's empty or whose elements can be numbered. You can give them a number, give them a student ID. All right, 1 through n for some positive integer n. So there's a stopping point. There's a largest number of elements in this set. All right. If it goes on forever, it's an infinite set. You can't give them all numberings that end eventually. And if you'd like to talk about finite sets, now let me just give you an example of an infinite set, all of the positive numbers. That's a standard example that people like to use a lot of the time in math. People consider the set of all the positive numbers and then they do something with it. All right, so that's an infinite set. And the fancy term for how many elements are in my finite set is called cardinality, and it's you use the absolute value symbol. So A, for example, has 3 elements, and so its cardinality, we say, with this symbol, is 3. Okay? There's 3 things in it. It's like got size 3 kind of thing. So that is some more notation. Now I have some cool symbols to teach you. So N and Z are probably the more important ones, so I'm giving you those first. N is called the set of natural numbers. It's an infinite set. It's all the integers greater than or equal to 0. So it's this set, 0, 1, 2, on and on and on until the end of time. And the reason it looks so cool, like this is an N, it's called a blackboard bold N. It's like teachers back in the day, like in textbooks, in your textbook, this is a bold N. They use the bold N. Boop. But teachers writing on whiteboards or blackboards back in the day, they did not like want to take the time to like fill in their N, and so they started writing it like this, just to indicate that it's weighty and supposed to be thought of as the bold version that you see in your textbook. So this just became its own symbol eventually, and it's the set of natural numbers. You'll see it like this in my slides, and also as bold in your book. So just keep that in mind. N is the set of natural numbers, all integers greater than or equal to 0. It is this set, on and on forever until the end of time. Some people, this is a source of debate for mathematicians, like whether or not 0 is a natural number or not. In this class, we are going to say that 0 is a natural number, because all things should start with 0 in computer science, especially. So some people think that the natural numbers start with 1, but we're going to tell those people that they are wrong. We are going to fight them. All right, so 0 is the first natural number as far as we are concerned in this class. And it goes on and on after that, all the integers. 0 onwards, all right? So yeah, the style is called blackboard bold. It's supposed to be a bold N, but nobody wanted to write that. We next have the set of all the integers. So if you want all the non-negative integers plus the negative integers, there's a word for that. There's a set for that. That just you can write the letter Z in blackboard bold. Here's how I'll write it. There you go. Isn't that pretty? And it just means all of the integers, all the whole numbers, this way on to negative infinity plus 0 and 1 and 2 all the way to positive infinity. Okay, so again, it's an infinite set, and it stands for integers. It's from the German word Zahlen, which means numbers. That's why they gave it a Z. And then if you wanted just this set, right, just the set 1, 2, 3, 4 all the way to infinity, not including the 0, you could write Z plus. That's what people do. That's all the positive integers. So that's starting with 1 on and on forever. All right. So natural numbers, N is 0, 1, 2 forever. Z is every integer, and Z plus is every positive integer. Okay. So just some more notation. There's a lot going on in these slides. I have to show you a million different pieces of notation, but I promise with enough practice, they will all make sense. So these are just sets. They're things that hold things. Could be infinite. All right. Next we have Q and R. So Q is the set of all rational numbers. Q for quotient. So it's the set of all elements A over B, where A and B are both integers. You see how all this notation is making sense? A and B are in Z, and B is not 0 because you can't divide by 0. So Q is the set of all rational numbers. So you can have 0, 1/2, any number that has like decimal places that eventually ends, because this is just 523 over 100, right? -5/3. You can have whole numbers, right? You can have like 42, because you can write that as 42 over 1, yeah? So those are all your quotients, and so you'd build this set of every possible rational number, every possible fraction. Okay, and of course it's infinite. Just pick 2 numbers in Z and make sure that the denominator is non-zero, and you have a bunch of different possibilities for rational numbers. All right, so that is Q. Then R is the set of all real numbers. Also very, very important, especially in like your calculus classes. All of your functions operate on real numbers. So what the real numbers are is Q, all the rational numbers, plus all of the irrational numbers. So that's how you make the real numbers. You got your normal numbers that are rational, and then you have your irrational numbers, like pi squared root of 2. That makes every number on the number line, right? That's how it works. So that is R. It's just all these things jumbled together, on and on and on until the end of time. That's just a giant set. Okay, so your book is always going to use bold, and I will probably always use Blackboard bold because you need to learn it, and I think it's really pretty. So here's how I'll write all of those symbols. Okay, that's the idea. So yeah, those are some more special sets. We're still not done with notation. I am so sorry. You will read more about it in the book, and I just need to get it across to you on the slides too. So let me show you different ways to talk about sets. So it's called set builder notation. That's one way to do it. If you would like to create a smaller set from a larger set, like you have some starting set, call it S, and you'd like to make a set A from S, take all the elements of S, only the ones though that have this predicate return true. All right, so this is how you define that. You put a little colon, you're like A is equal to all the x's in S such that P of x is true for that x. All right, so A is all the x's in S such that P of x is true. Instead of a colon, you might also see just a pipe character, and so that's the same. It's interchangeable. And so here's another set that kind of makes sense. It's every even integer. Do you see how I'm reading that? So B is equal to every x in Z such that x is even. Okay, so that is how you build sets from larger sets. So you have this large set Z, that's every integer, but I just want to pick out some of those. I want to pick out every even number, so like all the negative even numbers, like -2, -4, 0, +2, +4. That's what B holds now. Okay, I hope that makes enough sense. Let's see here. Next you have the universal set. This is usually when you're talking about something being in a set and something being outside of a set. The universal set is kind of like the stuff outside. It'll make more sense with an example, but the universal set is supposed to be the set that contains all of the elements mentioned that are in your context, which is sometimes implicit, unfortunately. So like if we're talking about integers and we're doing stuff, we're making sets of integers, maybe the universe then, the universe of discourse, that's another way to say it, is Z, all the integers. Okay, but this will make more sense with more examples. It's a little weird to think about. Once we get to the minus operation on sets, it should be very apparent. Yeah, but there is always a context. Sometimes, unfortunately, it is implicit. And then finally, Venn diagrams, which you know and love already. All right, that's just pictorial representations of sets. It's ways to draw sets. So you've already been doing these. So A, for example, is the set 1, 2, 3, and B is the set 2, 3, 4, and you could draw these in a way that helps you understand like what's going on. A is 1, 2, 3, and what do they share? Does that make sense? So these are Venn diagrams. You know them already. You can see like what their differences are and what they have in common. That's pretty cool. We're almost done with notation. All right, some operations now that you can do on sets. Because you can make bigger sets, because you can make smaller sets from bigger sets, a lot of the time you would like to express the fact like this set is larger. This set has all of the elements in this one set and some more. All right, so there's a subset and superset kind of idea going on there. It's like the set equivalent of less than and greater than. So let's talk about subset first. A set A is called a subset of a set B if and only if, by the way, if and only if for every x, for every element x, if x is in A, then it must be in B as well. All right. So everything in A is in B, and then B might have more things. All right. So for all x, x is in A. If it is in B, x is in A if it is in B. I might have got that backwards. I'll have to think about that. Let me just type it out. If x is in A, then it is in B. That's what I should be saying. Okay. If x is in A, then it is in B. Every element of A must be an element of B, therefore, right? So for example, let's see here. Here's a set A, 1, 2, 3, and here's a set B, 1, 2, 3, 4, 5. A is definitely a subset of B. This is true for every element, right? So let me draw that out. A is, let's see, 1, 2, 3, 4, 5, or it's just 1, 2, 3, excuse me. 1, 2, 3, and then B is the 1, 2, 3, 4, 5. Whee! So there's a bit more over here in B, but do you see how every element of A, if it's in A, then it's in B. Yeah, here's 1, 2, 3, also in B. B might have some extra things though. Okay, I hope that makes sense. Notice that if the sets are equal, or if the first set is empty, that is also how it works. Those are also subsets, right? A is a subset of itself. A is totally a subset of itself. Do you see that? Because if every element in this better be in this, yeah, of course, they're the same set. And then also, the empty set, totally a subset of any set, because like, are all these elements in here? Yeah, there are no elements in this side. It's called vacuously true. Okay, that's a little weird, but with enough examples it makes sense. But this is subset. Every element of A is also an element of B, and B might have more. Okay, that's how you remember it. So A is a subset of B, A is a subset of C as well, and they're the same set, right? Is every element of this one an element of this one? Yes, absolutely. Same for empty sets, a subset of everything. And this is how it's written. It is essentially the operation less than or equal to on sets. Do you see how it's very similar? Like they just curved it out. That's how subset works. And just like in addition to less than or equal to, you can have strictly less than. In addition to subset, you can have proper subset. You can get rid of that little line on the bottom there. And this is called a proper subset. A is a proper subset of B if and only if, for all x, if x is in A, then it's in B, and they're not the same. A is not equal to B, all right? So there's no equality going on, and you get rid of the line, you call it this. It's a proper subset. And it's very similar to strictly less than. You see that? So A is totally a proper subset of B, because B has more elements, but it also has all the elements of A. All right. The empty set is a proper subset of B, because they're not the same set. Like empty set's much smaller, and all of its elements, there aren't any, they're all in B. Yeah. So that is a proper subset. And then you could write a slash through to indicate that it's not true. So A is not a proper subset of C, because they are equal. They hold the same elements. You see that? So that's how that works. And then likewise, the idea of superset is just greater than or equal to. Okay? A is a superset of B if B is a subset of A. It's just you flip it around. Okay? You write it like this, going the other way, and I think you understand that proper superset means exactly what you think it means. All right? So C is a superset of A because all the elements of A are elements of C, because A is a subset of C, and vice versa, actually. B is a superset of A. It's got more elements, and it also has all the elements of A. All right? So it's very similar to what you have in your mind when you're thinking about greater than, just in terms of elements rather than like a spot on the number line. I hope that those examples are causing things to make a bit of sense in your brain. Let's keep on trucking, and then I have some examples for you to practice with. All right, so first idea, let's understand how we can prove stuff. How can we prove that one set is another? That is usually something that we would like to do, right? So let's pretend we have two sets, A and B. How do we prove that A is equal to B? Well, kind of the same way that you prove two numbers are equal. If you know, like x is equal to y when, right, x is less than or equal to y, and y is less than or equal to x. The only way that this could be true at the same time, right, is if they were equal. And you could use the same trick on sets. A is equal to B when A is a subset of B and B is a subset of A. That means they have A shares all of B's elements, B might have more, and then B shares all of A's elements, and A might have more. That means everybody has the same stuff, okay? The only way for that to be true is if they're equal. So, and we know what it means. Like, we can expand these definitions, including those for alls that we were talking about. So let's expand that. So A is equal to B then if, for all x, if x is in A, then it's in B, and if x is in B, then it's in A. See how that's working? And so we can combine these, you remember, to combine two implications, one going in each direction. A is equal to B if and only if, for all x, x is in A, if and only if x is in B. See how they must be the same? If x is in A, then it must be in B, and vice versa. If and only if is a great way to express that idea. Okay, so that's just math, getting into the symbols, and now I finally have some examples for you to try. Okay, so give this a try, and let's see what you're thinking. All right, so we got these two sets. A is equal to this, and then B is equal to this. B is equal to all the x's in Z, so every integer, such that x is an integer multiple of 42. Interesting. All right, so x starts out being every whole number, but we're like filtering out only from those all of the integer multiples of 42. So that means essentially another way of writing this in set builder notation is B is like all the multiples of 42. It's like 42 times x for every x in Z. See how that's another way of writing that? So it's every multiple of 42, which is essentially like, what do we got? We got 0. 0 is a multiple of 42. 42 is, of course, a multiple of 42. 84. It's also integer multiples, so like -1, -2 times that. So like -42, -84, and on and on and on forever. So that's what B is. It's an infinite set, and here's what A is. All right. So let's answer these questions now. Is 1 in A? Is 1 an element of A? Yes, it's right there. So yes. Is 5 an element of A? No. It's really not too bad, right? Is the set containing just 42 and 84 a subset of B? Are all of those elements in B? Absolutely. There they are. Is 1, 2, 3 a proper subset of A? See how there's no line there? It's a proper subset. So, are all of these elements in A? Yes. But are these sets non-equal? No, they are equal. So no. But it would be if you just use normal subset. But it is just a normal subset. It's not a proper subset, though. All right. And then finally, what is the cardinality of A? That's just asking how many elements are in the set A. And that answer is 3. There's 3 elements. Okay. I hope that is pretty clear. Just get in practice with the symbols. All right, try these. These are a bit fancier. Is it true that R is a superset of Q? So these are the real numbers. These are the rational numbers. Maybe you want to go back and rewind or check the book. What does that mean? And then, is Z plus a subset of N? Tell me yes or no. What does that all mean? So Q is, what is Q but all the rational numbers, right? And what is R but, I think R is the one I really wanted to write. R is equal to all of the rational numbers, right? All the elements of Q plus all the irrational numbers. So, is it true, like if you just flip this around, it's asking is Q a subset of R? It's the same as asking if R is a superset of Q. Is it true that all the elements of Q are in R? Well, yeah, it's defined like that. So this is a true statement. I hope you see that. And then also, is Z positive? All the positive numbers a subset of all the natural numbers? So remember that this is all the numbers that are positive, all the positive whole numbers. And then remember that N is all of the non-negative numbers, so 0, 1, 2, 3. So onward and upward. Are all of these elements in here? They sure are. All right, so 2 truths. I hope that is clear. All right, let's keep on trucking, because we're doing some things with sets now. I think you can kind of get a glimpse of how they're useful in defining all of mathematics, but there's plenty more ways that we could combine sets and do cool stuff with them. All right. So the first really cool thing that's pretty necessary is that you can put sets in sets, because what is a set but something that can hold things? It can hold anything. All right, so A, we can define A to be a set consisting of the set 1, 2, the empty set. You can put the empty set inside of another set, the set 1, 2, 3, and also the set 1. So all of these inner sets are inside of the set A. Does that make sense? And then things get a little weird because this is now an element. 1, 2, the set 1, 2 is an element of the bigger set A. 1, 2 is in A. It really is just an element, which may be a little weird since we were using like subset with 2 sets kind of before. No, this is fine. It's an element. The empty set is in A. There it is right there as an element. Okay? The number 1, though, this is where it gets interesting. The number 1 is not an element of A, because like this is an element, this whole thing, this is an element, this is an element, this is an element. The set 1 is not the same as the number 1. Okay, I hope you see that. Those are non-equal. So like this is the number 1, and this is the set containing 1. They're not the same. All right, so 1 is not in A. It would be the set 1. That's the thing in A. Okay? And 1 is in that. Now, that is not too bad. And then also you can make things called the power set, and nobody agrees on whether or not that should be 2 words or 1, so I'll use them interchangeably. The power set of a set A is the set of all the possible subsets of A. Okay? So people like to write this as P of A. Your book should be using italics, but they are not. Maybe they've changed it so far since I last looked. But at least last semester it was not italics, sadly. So P of A represents the power set of A, all the subsets of that set. All right. So if A is this, if A is the set 1, 2, 3, here are all the possible subsets of A. Oops. The empty set is a subset of everything. The set itself is always a subset of itself. And then here are all the inner non-equal, non-empty subsets of A. So like the set with just 1 in it, that's a subset of A. The set with just 2 in it, that's a subset of A. So all the individual elements by themselves, those are subsets, as long as you put them in a set. 1, 2 is a subset of A, right? Those are 2 elements taken from it. 1, 3, that's another 2-element set taken from A. It's a subset. Same with 2, 3, and then all the way up to 1, 2, 3. All right, so I hope you see that these are all the possible subsets that you could make of the set A. And a cool thing about this is the power set has to do with taking 2 to the power of something. So if the cardinality of A is n, here it's 3, then the number of subsets of that cardinality 3 set is 2 to the 3. It's like every option. So it's 2 to the n. So there must be, therefore, 2, 4, 8 elements of this subset, and of course that is right. All right, and the proof for this, like if you have this subset and you take its power set, all the different, how many subsets does it have? Well, it's 2 to the n, because for each element you have an option, right? Like the 1, for every subset that you're making, you have an option. Do you keep it? Do you put it in the current subset that you're making, or do you leave it out? Right? Either include it or don't. And so you have 2 options when you're making this set. When you're making a particular power set element, a particular subset, do you include the 1? You also have another option here. Do you include the 2 or keep it out? So you have 2 options here, 2 options for the 2, and then also 2 options for the 3. Do you put it in the subset that you're making, or do you keep it out? So 2 options times 2 options times 2 options, that's 2 to the 3. All right, 2 cubed. And that is my hand-wavy proof for why that works. You can make that a bit more formal if you'd like to, though. But that's power sets. And let's see, is that everything that I wanted to say here? I do not know. I have 2 copies of this slide. Sorry about that. That's a little weird. I think I can safely delete it. There is no difference, right? Yeah, sorry. Don't know what was going on. Maybe I accidentally copied it. All right. So, with that in mind, let's see. What could I do better? I think I could... Let me draw some more stuff for you before we leave. So here is... let me draw this exact set for you. I think that would help. Help drive it home. So that was all that stuff down there, kind of. Put it away. And then up here, let me just draw that A. This is what the set A is doing. So here's the set A. Whee. And so it holds. This is a big giant blob of the thing, right? A, the set, holds the set 1, 2 inside of it. It holds the empty set inside of it. It holds the set 1, 2, 3 inside of it, separate. And then it holds the set 1 inside of it, all right? So this is the set containing 1. And it's not the same as the number 1. If that were true, then 1 really would be an A. But it's the set containing 1 that's an A, not just the number 1. Okay? That, I hope, makes it a bit more clear. All right. Here's a funny meme example of the empty set versus sets containing the empty set, because there are two different things. So here is, let's see, keep it blue for here. This is the empty set, just a Tupperware without anything in it. It's empty. And then here is a set containing the empty set. Do you see that? See how they're not the same? It's a Tupperware with an empty Tupperware inside. There is an element of this outer set. It is the empty set, which is really weird to think about, but I promise it really works. So like A, you could define A to be the empty set. And another way of writing that, remember, is just two parentheses by themselves. That's not the same as this B, which could be the set containing the empty set. See that? You would write that as like two curly braces, because here's the empty set. It's inside of this set, right? So this outer set is not empty. It's not empty. It's holding an empty thing, though. It's holding the empty set. With enough practice, that will be not confusing, but I can imagine how confusing that is right now to you. You will get through it, and I will help you. All right? So here are some examples that I'd like you to try now, given these new terms. And then we will take a look at what you're thinking. So here's a big set. It's got all these things in it. Some are just elements. Some are other sets. So tell me what the cardinality of X is. Tell me if 2 is an X. Tell me if 2, 3, the set 2, 3 is a subset of X. Tell me if the set 5, 6, 7 is an element of X. Right? And then do the other ones while you're at it. What is the power set? What is the power set of the set containing 8, 9, and 10? And then what is the power set of the empty set? So do this inner one first, and then try to take the power set of that. I promise that this one is not as hard as it seems, but you will have to think about it. All right? So, assuming you gave these all a good try, let me show you how I might think about them. So what's the cardinality of X? That just means how many elements of X are there. So if this is tripping you up, there's not like 7 elements, you can always just draw a picture. So what is X? But it's got 1 in it. It's got the set 2, 3 in it. It's got the element 4, and it's got the set 5, 6, 7 as its last element. And so there's 4 separate elements. You see that? That's the cardinality of X. Is 2 an element of X? So, like, is there a 2 floating around? Absolutely not. It's part of a bigger set, but that is not what it's asking. Is 2 by itself an element of X? No. This is an element, this is an element, and so are these last 2. None of those are 2. All right, so the answer is no there. Is 2, 3 a subset of X? All right, so this is a tricky question, because look at 2, 3, it's there. But 2, 3 in this case is an element of X. It's not a subset, all right? So this question, it's saying like, is 2, 3 a subset of X? It's asking, is 2 an X? And is 3 also an X? You see how it's asking that? That's what it means to be a subset. Like, all of these things better be elements of X. That's not the same as what you're seeing there, all right? So this implies, if this is true, implies that both 2 is an X and 3 is an X. And neither of those are just laying around. All right, that's not what it means to be a subset. So the answer is no. All right, it would be yes if they asked this, right? If they asked, is the set 2, 3 an element of X? That one is true. But the set 2, 3 is an element of X. There it is, just by itself. All right. And so with that in mind, I think this answer should come to you. Is 5, 6, 7 an element of X? Yes, here it is. It is a single piece inside of X. A single element. All right? So that is that example. All right, and now let's talk about power sets. What are all the power sets of the set 8, 9, 10? And it should be very similar to this one. It's the same number of elements, so you should see 8 elements, right? And that's how that's working. So let's see here. What are all the elements of the power set of the set 8, 9, 10? And so the empty set is always a subset. What are all the subsets? Empty set is a subset. It's in the power set. And then you have all the single-sized subsets, so just 8, just 9, just 10. Taking this class will get you very good at drawing curly braces. And then you have all the 2-element subsets, so like 8, 9 is a subset. I am still not an expert on the curly braces, obviously. 8, 9 is a subset, 9, 10 is a subset, and then 8, 10 is another subset. And then you have just all of them, like the whole thing is a subset of itself, so 8, 9, 10 is also in the power set. Okay? And that should be 8 elements, 2 to the 3, right? That should make enough sense. Oh, I just remembered. Another way to describe this, to keep it like that, it's kind of asking, is both of these elements, are they both in X? This is the thing that's true, and you could write this thing like a subset, all right? You could go from here to, this is getting a bit unwieldy, sorry. What does this mean? It means that the set containing the set 2, 3 is a subset of X. So if you wanted to use subset really, and you wanted to say something that's true involving the set 2, 3, you'd have to put it inside of a set. It's like, because what does this mean? Is this in X and is this in X? No. But is this in X all by itself together? I think I accidentally forgot a curly brace, sorry. Is this in X? Yeah, it is, okay? Is also true. So you will get lost in notation for a little while, but I will help you out of it, okay? So here's the last question, probably the hardest one here. What is the power set of the empty set? And so you have to think about this. It's very odd. And I encourage you to start from the inside out. So what's the power set of the empty set? Well, if you're not even sure, let's see here. What is the power set of the empty set? If you don't, if you're not sure, think about what has to be always a subset. Like the empty set, what are all the elements? How do I make subsets of the empty set? What is always in the power set? The empty set is always in the power set. It's a subset of everything, including the empty set, okay? So that's the first hint. The empty set must be in the power set of the empty set, no matter what, all right? And then you can ask, like if you're not sure how many other things might be in there, you can go back to this rule. If you have this size of a set, the size of its power set is equal to blank, 2 to the size of the original one, all right? So if I don't remember all the elements of the empty set, or all the subsets of the empty set, if I'm not sure, if I think there might be more, then what is the size of this? It better be equal to 2 to the size of the empty set, which is 0, right? There's nothing in the empty set, so 1. So there's one element in the power set of the empty set. It's just the empty set. This is the only thing that's a subset of the empty set. I hope that makes enough sense. Okay, so now I have that this is the power set of the empty set. And now I need to compute the power set of that. The power set of the empty set, which is equal to the power set of, let me draw some lines between these things. Whee! Which is equal to the power set of this, the set containing the empty set. What is immediately always in the power set of anything? The empty set. And then, all right, let's do our math. What is the size? What must the size of the power set of the empty set be? Well, it's 2 to the size of whatever this is, all right? How big is the power set of the empty set? It has one element. There's its one element. So it's 2 to the 1, which is equal to 2, all right? So this is an element of the power set of the empty set. This is an element of the power set of the set containing the empty set. See, even I get lost in the words. The symbols make it all make sense. There's one more missing element. It has to be 2. And so you have to think about it, all right? What are all the elements here? So the empty set is always an element of the power set, and then also the original set is also a power set of that set of itself, okay? So what have I forgotten? This. That was the original thing. That was the original set. So that goes in the power set. Those are my 2 elements. And that's the final answer. okay? Because remember that these are two different things: the empty set and the power set containing the empty set and the set containing the empty set. Too many words. Those are not the same thing, and so they're separate but together in this final output, okay? And so when in doubt, remember that the empty set's always there, remember that the original set's always there, and then remember that your sizes can help you here. Like, I knew I needed something else. What did I forget? Then you can check. So this is probably the hardest question. Hopefully my explanation makes enough sense. Please yell at me in office hours or on Discord if it did not, and I will re-explain it a different way. All right. Finally, this is probably the thing you're going to want to do most often to sets. We took us so long to get here. We're finally ready. All right. So you can union two sets and you can intersect two sets. It's very, very common operations that you'd want to do on your sets. So a set union is when you have two sets and you bring them together. You join two sets to make a bigger one. All right. So A union B. Look at how this kind of looks like an OR. It's actually defined using OR. That's why. Just a curvy version of everything with points. So the union of two sets A and B is all of the elements X such that X is either in A or it's in B or it was in both. All right. So A union B contains all elements that are in either A or B or in both. All right. So here, let's pretend that here's my silly example of A and B. So A is 1, 2, 3, and B is 2, 3, 4. So there's A, there is B, and I'm going to use this same example in the intersection, so I'll just put that down here too. So what is the union of all the elements of A and B? What's A union B? Well, it's the set containing all of the elements in A or in B. So it's just this bigger set. You see, it's everything in both. 1, 2, 3, 4. That's the union. Okay? That's how that works. The flip side of that, the exact opposite of that, would be the intersection of two sets. It is the upside down U. It's like a cup or something, like a wedge almost. And so this, notice how that looks a whole lot like and it's defined using and. It all makes sense. So intersection takes out the common elements of two sets. So A intersect B is all the elements X, such that X is in A and it's in B. All right? It contains all the elements that are in both A and B. It's all the stuff that they share. Okay? So again, with the same example, what's in their intersection? It's all the things that they have in common. What's in A and B at the same time? It's the 2 and the 3. Do you see that? So this is the intersection. Those elements are 2 and 3. A intersect B is the set containing 2 and 3. Okay? That is the trick. So, what do they share? These guys. Just like that. Okay? And I want you to use that similarity between the symbols to help you understand what's going on. So, union, or. It's defined using or. It's like, is the element in one or the other or both? Intersection is defined using and. Is this element in both at the same time? Is it in this one and is it in this one as well? Okay, so that's union and intersection. I'm sure you've used these, maybe just not having known that they were called this, when you were working with Venn diagrams before. All right, so a final, hopefully not too hard question to wrap up today's lecture. What do we got? 3 sets. Do these operations, please. Remember, parentheses tell you what order to do stuff in. All right, so what's A union B? Well, it's all the stuff that's in A or B or both. Remember that no duplicates exist in sets, so it doesn't make sense to write 3 twice. So what is an A union B? Well, 1's in A, 2's in A, 3's in A. It's all those things, and then everything else in B. So 3 I've already written, then 4, then 5. It's anything that they both have, or anything that either one has. Okay? There. Pretty ending curly brace. What is their intersection? What does A intersect B? And that's asking what do they have in common, right? What do they share? Well, 1's not in B, no. 2's not in B, 3's in B. And that's actually, you're done at that point. But you can go from the other perspective, like, yeah, 3's in A, 4 is not in A, 5 is not in A. Okay, so it's the 3 that they share. And so that would be your answer. What's their intersection? It's just the set containing the number 3. That's the only thing. Okay? So union and intersection create a new set for you. All right? And so this one, what's an A union B intersect C? Well, you got to do B intersect C first. What's that? It's all the elements that are in B and C that they share. So it looks like it's the 4. The 4 is the only thing that they share. And so take that and union it with A. What is the union of the set containing 1, 2, 3 and the set containing 4? Well, it's the set 1, 2, 3, 4, right? Any element that any of them have, the union takes. All right, so that's the final answer there. And so that brings us to the end of our first lecture on sets. I'm sorry there were so many new terms. It's really hard to keep them straight, but with enough practice, the symbols are the things that help you, okay? Even I get tripped up still talking about it. But the symbols tell you exactly what's going on, and that's what I want you to pay attention to. All right? So we'll be back in the next lecture to continue this, and that'll be that. So I'll see you then.